Hi everyone. Now that we're going to be working more and more on FRQs, we wanted to make sure we had a really explicit discussion about units in calculus, because units are going to be a big part of the reasoning and justification that you're going to have to do in these FRQs, so we want to make sure we went ahead and talked about that. So throughout the next chapter, we're going to be applying our calculus ideas to real-world applications. So for most of the questions you'll be asked, you'll be required to explain the meaning of your answer in the context of the problem using correct units. Now, when we're talking about these explanations you're going to have to write, there's going to be a few parts, kind of a few things that the College Board's going to be looking for in your responses. So when you're writing these explanations, the first thing you're going to always want to put in your explanation is you're going to want to state what you measured or calculated. Once you've done that, you're going to want to write a description using appropriate vocabulary. And as we go through some of these problems, we'll talk about what that vocabulary might be depending on the problem you're working on. And then the final thing you're going to want to make sure you include is the value you found, including correct units. So all three parts are going to be really important in ensuring that you have a complete explanation. All right, so the first thing we're going to look at is problems involving derivatives and how units work with these types of problems. So earlier this year we used units to describe our answers in the context of position, velocity, and acceleration problems. So example, for velocity, when we talked about velocity, oftentimes we had units like meters per second, and when we talked about acceleration, we would talk about meters per second squared. So units have come up, but they're going to start playing a much bigger role. So when we find a derivative, remember we're focusing on derivative problems here. When we find a derivative, we're finding the instantaneous rate of change, or the slope. So to determine the appropriate units for a problem where we use a derivative, it's helpful to think of this as a ratio. So let's take a look at a specific problem that has come from an FRQ. So here our scenario, it says the height of a tree at time t is given by a twice differentiable function h. So here I have my values for the height, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table above. Now it says use the data in the table to estimate h prime of 6. So that's the first thing we're going to do, is just using the data to estimate h prime of 6. Now, as soon as I see this derivative here, we know a derivative is a slope. Specifically, it's a slope with a tangent. So if I had a function, we would take the derivative and then plug in 6. Now in this case, we don't have a function. All we have is a table. So since we don't have a function, all we can do is estimate that derivative. And we're going to do that by using our old kind of definition for slope. So h prime of 6, now if I look in the table, I know 6 is here between 5 and 7. So if I take the average rate of change between 5 and 7, that'll approximate that instantaneous rate of change at t equals 6. So this is approximately, we would say, h of 7 minus h of 5 over 7 minus 5. So h of 7, I grab that from the table, is 11. H of 5 is 6. On the bottom I have 2, so I get 5 over 2. Now, if I'm thinking about units, I have my values of h on top. I know that unit is meters. And then I have my values of time on the denominator. Units are years. So I have 5/2 meters per year. So that's our estimate for h prime of 6. Now it says using correct units, and we've already kind of done some of that analysis. Using correct units, interpret the meaning of h prime of 6 in the context of the problem. So here's where we want to kind of think about the three things that we stated up here that we need to include in that interpretation or that explanation. So first we said state what you measured or calculated. So in this case, we know we were talking about the height of a tree. So I'm going to say the height of a tree . The height of the tree. Well, let's see what we know. We know this derivative is giving us a rate. All right, the derivative is telling us about a rate. So it's the rate at which that tree is growing. Now, since this is a positive rate, we would say the height of the tree is increasing at a rate of 5/2, 5/2 meters per year. So again, going back through that, for part 1, we stated what was measured or calculated. So we were talking about the height of the tree. For our description using vocab, here it was important. First, we mentioned rate. We mentioned that that rate was increasing, and again, we knew that because h prime of 6, let me write that again, sorry, h prime of 6 is greater than 0. So we have our vocab increasing and our rate, and then for the last part, the value that you found, including units, that was our 5/2 meters per year. So that's what our interpretation would be. The height of the tree is increasing at a rate of 5/2 meters per year. Now, one thing I want to bring up here, and this is an aside from this problem. Let's say we took a derivative, and so this is totally separate here. Let's say in a different context, maybe we are finding a derivative. So let's just say dy dx, and let's say we got a negative number. That rate was less than 0. If we were writing an explanation, so let me say instead of less than 0, let's say it was -2. So if I had to write an explanation, in this case we would say whatever was happening, we would say it is decreasing. So whether it's the height of a tree or some other scenario, that would be decreasing at a rate of 2, and then we would put in the units. What I want to point out here is that this negative tells us that we're decreasing. We don't make this a -2. It's decreasing at a rate of 2, but the negative tells us it's decreasing, and we don't include the negative in our value. So that'll come up, so I wanted to make sure I mentioned that here. All right, so the first problem was a no calculator problem. Let's go ahead and look at the second one, which is a calculator problem. So here our scenario, and again this came from an AP exam. When a certain grocery store opens, it has 50 pounds of bananas on a display table. Customers remove bananas from the display table at a rate modeled by this function. So I'm going to make myself a note. Let's see, this function is the rate at which customers remove bananas. So it's not the number being removed, but it's the rate at which they remove them. All right, so F of t is measured in pounds per hour, and t is the number of hours after the store opened. So here we're being asked to find f prime of 7, and then again, using correct units, explain the meaning of that answer in the context of the problem. So let's start off with f prime of 7. Now, since this is a calculator problem, we're just going to go ahead and enter this in our calculator. So hopefully you remember to do a derivative, excuse me, let's see, we're going to do math, and then we're going to do 8. This is going to give us our derivative notation here, and we're going to enter this in just like we see it in the problem. So derivative with respect to x, even though we have t's in here, we're going to use x in our calculator. So 10 plus, I'm going to use my parentheses in just the same way, 0.8x times the sine of, let's see, x cubed divided by 100. Okay, and then we're looking at our value here. It's f prime of 7, so we're going to do that when x equals 7. Let me check one thing. Okay, good, I'm in radians, so I'm okay. All right, so f prime of 7 we have is approximately negative 8.1. Let's see. Now, AP for the exam, you can either just cut it off after 3 places, so 119, or we could round and say negative 8.120. They will accept either answer. So we've got f prime of 7, and now we have to explain the meaning of that value in the context of the problem. So we were looking at here the rate at which customers remove bananas. So we would say the rate at which customers remove bananas. Now here, since I have a negative value, and this is what we talked about earlier, we would say the rate at which customers remove bananas is decreasing at a rate of 8.120. Again, I don't say decreasing at a rate of negative. We just know that negative means decreasing. And now we have to think about bananas. Or excuse me, not think about bananas, think about the units. So we could think of this derivative as a ratio, right? So our function, let's see, was measured in pounds per hour. Let's do this, pounds per hour. And then time was measured in hours. So we can say pounds per hour, or we can say pounds per hour squared. And that would be a complete explanation. Okay, so that's the derivative side of this. Let's flip over now and look at units with integrals. Here we go. All right, so now when we find an integral, we are finding the area between a curve and the x-axis. So to determine the appropriate units for a problem where we use an integral, it's helpful to think of this as an area problem. And I'll kind of get into more of what that means as we go through here. So actually, let's kind of talk through this. So let's say we were looking at a function and we had a rate on our y-axis. Let's say that was measured in meters per hour. And then our units on our x-axis were hours. So when we do an integral, we know that's an area. And what we're doing is we're multiplying really the base here, that would be measured in hours, times the height, which is measured in meters per hour. And so when we do that analysis, our hours are going to cross and we're just going to be getting meters. So that's what we mean when we think of this as an area, that you're multiplying those units together. All right, so let's look at the first problem, and these are both going to be calculator problems. So it says water is removed from a tank at a rate modeled by R of t liters per hour, where R is differentiable and decreasing over this interval. Select values of R of t are shown in the table above, and then it's giving us some initial condition. It's saying when we started, there are 50,000 liters of water in the tank. So now it's asking us to use a left Riemann sum with the 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. So we're using that Riemann sum to estimate the area. So we have 4 subintervals, so we go from 0 to 1, 1 to 3, 3 to 6, and then 6 to 8. Now, since we're using a left sum, we want to take those left endpoint values. So at 0, I have 1,340. 1 is 1,190. 3 is 950. And 6 is 740. So now I'm going to take my base times my height for each subinterval. So I have 1 times 1,340 plus 2 times 1,190 plus 3 times 950 plus 2 times 740. And then we're going to use our calculator to total those up. And we get 8,050. So now here's where we have to think about units. So maybe if we go back to our work here, we know these values along here, these are given to us, this is measured time. And now my function values here are measured in, oh actually I'm going to say time, but I'm going to specifically say measured in hours. And then our function values are liters per hour. So since we're multiplying these values, what we're really saying is we're taking hours times liters per hour. So we know now that our hours are going to drop out and our units would be 8,050 liters. So that would be the first part. So the estimating the total amount of water, that would be our answer. And then just like before, we need to give our answer using correct. Oh, I guess it doesn't ask us to explain. But let's go ahead and write it anyway just to stay in practice. This only asks for the answer with units, but let's go ahead and practice our explanation. So if they asked us what this represented, we would say the total amount of water removed from the tank. So we want to make sure we're writing nice complete sentences. So we would say removed from the tank. Now here we want to make sure we specify the time interval. So during the 8 hours, is approximately, now I'm saying approximately because we used a Riemann sum, which we know a Riemann sum is just an estimate. So it's approximately 8,050 liters. All right, one last problem, also dealing with integrals. So this one says, when a grocery store opens, it has 50 pounds of bananas on a display table. So we're revisiting the problem with our bananas. And again, we have our function, tells us the rate at which customers are removing those bananas from the table. So now this is asking us to find the integral and then give our answer using correct units. So we're going to find the integral from 0 to 2 of f of t dt. And again, we're going to use our calculator for this. So now we're going to do math 9 to get our integral from 0 to 2, and then we're going to plug in the function, excuse me. Dx, and we get 20.051. So now here again, we have to think about what our units are. So in this problem, and I'm just going to kind of do this maybe up here. So again, if I am multiplying, let's see, my time was measured in hours, so I'm taking in hours. Since this is an integral, I know I'm multiplying like I would with area. This is measured, my function in pounds per hour. So I'm measuring or multiplying hours times pounds per hour, which leaves us with pounds. So that would be the answer if they just asked us for the correct answer using correct units. Now again, just for practice, I want to add in the explanation. So we would say customers removed 20.051 pounds of bananas. Now here again we have to be really careful about specifying our time interval. So since it's from 0 to 2, we can say customers removed 20.051 pounds of bananas. There's a couple ways we could say this. We could say over the time interval. T equals 0 to T equals 2 hours. So that would be acceptable. I think in this problem, they specify 0 as when the store opens, so we could say customers removed 20.051 pounds of bananas in the first 2 hours after the store opened, but the important thing is just to make sure you specify that time interval in your answer. All right, so I know that was a lot, but these types of questions with units are really important when you hit the FRQs, so we wanted to make sure we did a pretty thorough job of discussing them. All right, thanks for hanging in with that, and I will see you when we are back in class.